Swayam Prabha. Digital India. Educated India.
Today I'll discuss about Pelton wheel, which is a hydraulic turbine, very old, simple in construction. Please note here the construction of a Pelton wheel, which is bucketed. However, it's still in use for power generation. So this is the discussion of a very primitive machines after discussion of very complicated turbo machines like multi-stage compressor and turbine, which are being used in aero engine or as gas turbine for power generations. So let's discuss on Pelton wheel now. The organization of the lecture, that is contents, are stated here. I'll discuss on introduction of Pelton wheel, then I'll derive the force on the pocket and power generation, followed by energy losses in a Pelton wheel, then specific speed and wheel geometry, governing of Pelton wheels, and then limitations. In this section, the governing principles of various types of hydraulic turbine used in hydroelectric power station will be discussed. I'll initiate the discussion with a Pelton wheel. The Pelton wheel is an impulse hydraulic turbine named after an American engineer, Lester A. Pelton, who contributed its development in 1880. Thus, considering the year of development, one can appreciate that it is an old prime mover. However, they are still in use. So let me tell you about the characteristics of the machines. So it is an efficient machine, particularly for high head and low flow rate. Thus, the Pelton wheel is a low specific speed machines rotating at low RPM. What are the advantages of a Pelton wheel? The advantages are good efficiency, operational flexibility, ease of maintenance. It is very easy to maintain, low wear and tear, a potentially inexhaustible supply of energy. That's very important. No atmospheric pollutions. Suppose please note that it will not create any atmospheric pollution like a gas turbine. I've indicated here the picture of a Pelton turbine with 21 buckets. Thus, Pelton turbine's rotor is having a circular disc with several buckets. Here, the two spoon-shaped buckets are joined, and there is a splitter. This splitter divides the impinging jet into two streams, and the steams gets deflected, and thereby there is change in the angular momentum which initiates rotation of the wheel. This is the operating principles of a Pelton turbine. Thus, I have sketched here illustrating the system of a Pelton turbine, where suppose we have natural source of water, and from the natural source of water a long pipeline is connected to the nozzle of the Pelton turbine, and this long pipeline is called the penstock. Thus the penstock leads water to the nozzle, and thereby the jet of high speeds is created, and these jets impinge on the buckets, get deflected, changing angular momentum and thus initiating rotation of the wheel. Hence, how indicated here, the rotor consists of a large circular disc or wheel on which several spoon-shaped buckets less than 15 are spaced uniformly around the periphery. Thereby, I have discussed here the rotor of a Pelton wheel in brief. In a Pelton turbine, the nozzles are mounted such that each nozzle directs a jet along a tangent to the circle passing through the center of the buckets, as illustrated in the figure 2. Please note the figure 2. I have forgotten to give the number here. Here I have illustrated the combination of the wheel and the nozzle, and please note that the nozzle creates jet that becomes almost tangential to the circle passing to the center of the buckets. And if we consider the D is the diameter of the jets, then the bucket geometry bears a correlations with D. I have already indicated these buckets are spoon-shaped and they are symmetrical. So please note that I have presented the side view of the buckets, where you can appreciate that bucket height is around 2.5 D and width is 4 D. And there is a splitter that goes up to down to the bucket, and this splitter divides the impinging jet as I have illustrated earlier, and the jet is almost deflected by an angle of 165 degree, which is represented here by theta, and theta is around, so theta can be thought about the camber angle. So here for a Pelton turbine, camber angle is 165 degree. Furthermore, the depth of the bucket is considered as 0.8 D. Thus, the geometric relations which can lead to the maximum possible efficiency of the turbine has given here. So these numbers, that 2.5 D, 4 D and 0.8 D that I am presenting here, which is the collections of data from number of experiments in reality. So thus I have indicated here, down the center of each bucket, a splitter divides the oncoming jet into two equal streams, and these two streams flow around the smooth inner surface of the bucket and leaves the bucket with a relative velocity almost opposite in direction to the original impinging jet. Please note that in practice, the water jet after impingement get deflected by around 165 degree so that the water while leaving the bucket may not hit back the oncoming jet. Therefore, the camber angle of the bucket is limited to 165 degree as I have already illustrated. Furthermore, the side thrust produced by the fluid in each half should balance each other since the buckets are symmetrical. Thus, I can say there will be no side thrust produced because of this deflection of jets. However, there will be tangential force due to the change of angular momentum that initiates the rotation of the hull. To obtain a high value of fuel efficiency, the bucket should have a smooth surface and be appropriately designed. Often the bucket's length, width, and depth are chosen about 2.5, 4, and 0.8 times of jet diameters, as illustrated in figure 2. Furthermore, the number of jets is limited to 6. I have indicated here a picture illustrating the 6-jet vertical shaft Pelton turbine producing a power of 174.4 megawatt, where the runner diameter is 4.1 meter and it rotates with a speed of about 300 rpm, having a head of 587 meter. Please note the numbers. Now I have illustrated a schematic indicating number of jets. Say here water is being collected and distributed to different jets almost equally, and after jets are being produced, then the pressure within the Pelton hull remains constant. Thus I have indicated here also that the flow partly fills the bucket. Here the impeller not fully filled like other machines, and once the nozzle produces jet, the static pressure of liquid remains atmospheric pressure throughout the machine, and hence the pressure within the impeller or the rotor remains constant, and thereby the machine is called the impulse machines. After a brief introduction on Pelton hull and discussion about its construction, I'll now try to explain the hydrodynamic action of fluid on a Pelton turbine, draw the velocity triangle, and derive the expression of specific work output and the efficiency of Pelton hull. In this slide, I'll explain the velocity triangle which would be appropriate for a Pelton hull. Please note that I have drawn the velocity diagram for one half of the bucket. Figure 4 here indicates the combination of the nozzle and the Pelton hull, which has already been illustrated. However, let me discuss here in brief. The nozzle creates the jet, and the jet gets deflected by the bucket, and the angle of deflection is around 165 degree, which is represented by theta. Thus theta is here is the camber angle. Figure 5 indicates the combination of a nozzle and a bucket, and thus jet impinging on the bucket and getting deflected has been illustrated here. So thus I have considered C1 be the absolute velocity of the jet which is created by the nozzle, and U be the bucket's speed. Therefore, W1 be the relative velocity at inlet to the bucket, and W2 be the relative velocity at exit from the bucket. And hence I have drawn the velocity triangle here in figure 5. So thus U plus W1 would be equal to C1, and U and W1 will be projected in a line which is the direction of motion of the blade. So after the velocity triangle and inlet, let me draw the velocity triangle and exit. Now at exit, I know W2 will be getting deflected by an angle theta. Thus, projected here U plus W2 is equal to C2, and thus I have indicated C theta 2. C theta 2 is the swollen component at exit, which is the projection of C2 in the tangential direction. I have also indicated the exit relative angle beta 2. Thus, I have drawn at inlet and exit velocity triangle which are appropriate for a Pelton wheel. After velocity diagram of a Pelton wheel, I will present here analysis of force on the bucket and the power generation. Let us consider that one jet is impinging on a bucket. The velocity diagram is indicated in figure 5 for a circumferential section at the mean diameter of the wheel D, capital D. Thus, please note that capital D here represents the mean wheel diameter. The jet velocity at entry is given by C1, while the blade speed is denoted by capital U. Then the absolute velocity of jet C1 with which it sticks the bucket can be expressed as C1 is equal to CV into root over twice G into HE, where CV is the coefficient of velocity which takes care the effect of friction in the nozzle, while HE is the effective head at the entrance to the nozzle, which is equal to the total or gross head of water stored at a high altitude minus the head lost due to friction in the long pipeline leading to the nozzle. Now, considering the velocity diagram, I can say that the relative velocity of jet at the entry to the wheel is W1 is equal to C1 minus U. That is the equation number 2. At the exit from the pocket, the jet leaves with a relative velocity W2, and here W2 makes an angle beta 2 to the direction of rotation. Hence, from velocity diagram, one can evaluate the absolute exit velocity C2. Now, from the Euler equation for turbine, the specific work done by water to the rotor is given by small w is equal to u1 c theta 1 minus u2 c theta 2. Now here u1 is equal to u2 is equal to uc. Thus the specific work done by water is given by small w is equal to, within bracket, c theta 1 minus c theta 2 into u, and is given by the equation number 4. Now from inlet velocity diagram, c theta 1 is equal to w1 plus u, and from exit velocity diagram, c theta 2 would be is equal to minus, within bracket, w2 cos beta 2 minus u. The negative sign here is given because, considering sign convention, c theta 2 is less than 0, or c theta 2 would be equal to negative, as it is in opposite direction of u. So thus c theta 2 becomes minus w2 cos beta 2 plus capital U. Hence the specific work output would be small w is equal to, within bracket, w1 plus w2 cos beta 2 into u. Now this is an impulse turbine. So here W2 would be equal to W1 without friction. However, if we consider the effect of friction, then exit velocity will be less than inlet relative velocity. Thus, I have written here, considering the effect of friction, W2 is equal to K into W1, where in reality K lies between 0.8 to 0.9. Thus, the specific work output is given by small w is equal to 1 plus k cos beta 2 within bracket w1 into u, which is equation number 8. Thus, equation number 8 gives the expression for specific work output. If Q is the volume flow rate of the jet, then the power transmitted by the water to the fuel can be expressed as P is equal to m dot into W, that is equal to rho Q within the bracket 1 plus K into cos beta 2 into W1 into U, where W1 is equal to C minus U, thus putting the value of W1, power transmitted by the fluid to the well, can be expressed as rho Q within the bracket 1 plus K into cos beta 2 within the bracket C1 minus U into U. So this is the expression of power transmitted by the fluid to the well, which is given by equation number 10. Now power input to the well can be found out from the kinetic energy of the jet arriving at the fuel, which is given by half rho Q into Swayam square. So therefore, the efficiency of the Pelton well would be is equal to energy output divided by energy input, that is eta W is equal to rho Q within the bracket 1 plus K into cos beta 2, again within the bracket C1 minus U into U divided by half rho Q into Swayam square. The numerator represents the power transmitted by the fluid, and denominator represents the kinetic energy of the jet arriving to the nozzle. So thus eta W can be expressed as twice within the bracket 1 plus K into cos beta 2, then again within the bracket 1 minus U by C1 divided by U, again U by C1. So thus the equation number 11 represents the efficiency of the whole, which depends on the velocity ratio U by C1, and the expression of this fuel efficiency is 2 within the bracket 1 plus k into cos beta 2, again within the bracket 1 minus u divided by C1, then into u divided by C1, and u by C1 is the velocity ratio. Thus, for a given design, I may consider beta 2 and k are constant. Thus, efficiency of the wheel depends on the velocity ratio. Thus, equation 11 indicates the efficiency of a Pelton wheel eta W. For a given design of the bucket, that is, we may consider beta 2 and k are constants, and hence eta W is the function of u by C1, which is the velocity ratio only. Thus, we like to find out the value of u by C1, for which eta W is maximum. To do that, I have evaluated d eta W by d u over C1 and put it to 0. While I do that, I have got twice within the bracket 1 plus k cos beta 2, again within the bracket 1 minus 2 u by C1 is equal to 0, which yields u by C1 is equal to half. That means for a velocity ratio u by C1 is equal to half, eta W becomes maximum. Further, please note that if we differentiate this further, that is d2 eta W by du by C1 square, then one can realize that double differentiation of eta W with respect to u by c is always negative, indicating that the equation 11 has only a maximum value. Thus, putting value of u by C1 is equal to half in equation 11, I'll get the maximum value of eta W, which is given by eta W maximum is equal to 1 plus k into cos beta 2 divided by half. That means the maximum efficiency of a Pelton wheel represents on beta 2 and k, and the value is given by 1 plus k cos beta 2 divided by 2. Through an example, I have illustrated the variation of theoretical values of runner efficiency with an optimum blade speed ratio of 0.5 when the k being 0.8 and 1.0 and beta 2 is 15 degree. Here I have illustrated that for k is equal to 0.8, the eta W max would be equal to 0.886, and again for k is equal to 1, eta W max would become 0.983. From this example, what we can appreciate that for a given blade speed ratio and relative blade angle beta 2, the different value of friction coefficient would give different maximum blade efficiency. Thus, there will be a change of maximum blade efficiency with respect to the change of frictional coefficient of the bucket. Now I'll illustrate the energy loss in the Pelton turbine. I've indicated here the schematic illustrating that penstock connecting the reservoir and the nozzle of the Pelton oil. Now let us consider with respect to a datum Z1 be the head available, or I can say Z1 be the level of water column of the sump with respect to the datum, and let us consider Z2 be the level where the Pelton oil is installed. Hence, I can see the gross head available Hg would be equal to Z1 minus Z2. Now the effective head would be equal to the gross head available minus the loss in the head loss rather in the penstock because of friction. Hence the effective head He available at the entry of the turbine is given by He is equal to Hg minus Hf, where Hf is accounted for the energy loss due to friction in the penstock. Now C1 is expressed as Cv into root over 2g into He, where Cv is the coefficient of velocity which takes care the effect of friction in the nozzle. Thus the primary losses of the turbine occurs in nozzle due to friction, and the second, converting kinetic energy of jet into mechanical energy of the rotor, and the third, the external effects because of bearing friction and windage. So that's what I like to tell. The energy losses can be divided in principle in three components. One is that occur in the nozzle, second that occur in the rotor because converting kinetic energy to mechanical energy, and third because of external effects such as bearing loss and windage. Now with respect to the item 1, that is nozzle loss, I can define here the nozzle efficiency, which can be expressed here that eta n equal to energy at the exit of the nozzle, which is indicated by the kinetic energy of the jet, divided by energy at the nozzle inlet, that is represented by the available head. So eta n can be expressed as C1 squared by 2 divided by G into He, which is the equation number 16. An often used alternative to eta n is the nozzle velocity coefficient Cv, and is defined as Cv is equal to actual velocity at the nozzle exit divided by ideal velocity, that is C1 by C0, which can be stated as C1 by root over twice G into He. That is equation number 17. Hence, comparing the equation number 16 and 17, one can say eta n is equal to Cv squared. The item number 2 defines the turbine hydraulic efficiency eta H. Thus, the hydraulic efficiency eta H is defined as the specific work done by the rotor small w divided by the specific energy available at the entry to the nozzle, that is G into He. Thus, eta H is equal to W divided by G into He, which can be expressed as W divided by half C1 square into half C1 square divided by G into HE. Thus, eta H can be represented as eta W, wheel efficiency, into nozzle efficiency eta N, which is the equation number 18. Therefore, equation number 18 says that eta H is the product of eta W and eta N. For item number 3, which says about the external loss, the external losses responsible for energy deficit between the runner and the shaft are due to the bearing friction and windage losses. Thus, the overall efficiency of the turbine is expressed as eta 0 is equal to shaft work divided by energy at the nozzle NT, which is equal to G into HE. And eta 0 should be product of eta N, eta W, and eta M being mechanical efficiency, which is equation number 19. The variation of overall efficiency eta 0 is illustrated as a function of speed ratio U by C1 for several values of windage losses kappa in figure 6. This is the figure 6, which illustrates the variation of eta 0 as the speed ratio changes for different values of kappa represent the windage coefficient. Please note that the peak efficiency reduces as the value of kappa increases, while it shifts at a lower values of speed ratio U by C1 than the optimum runner speed of 0.5. Note that as kappa increases, the maximum efficiency is shifted as indicated a dotted line here. Furthermore, the value of U by C1 usually obtained in practice is 0.46, while the overall efficiency lies in the range of 85 to 90% for large machines. Furthermore, one can easily appreciate from the figure 6 that to obtain high values of wheel efficiency, the bucket should have a smooth surface and be appropriately designed. Please note that Pelton wheel must run at a constant speed even if the load changes or the load fluctuates to match the grid frequency. Therefore, the governing of a Pelton wheel is a very important aspect which will be discussed now. The governing of a Pelton turbine has been illustrated here. The Pelton turbine is usually directly coupled to an electric generator, and thus it must run at synchronous speed. Therefore, the flow rate Q needs to be adjusted to ensure that the turbine runs at a constant speed despite of changes in load. The flow rate here is controlled by a spar or a needle valve using a servo mechanism. The needle is moved axially within the nozzle to alter the diameter of jet, and thus the flow rate as illustrated in the figure 9. This works well for very gradual changes in load. However, if there is a sudden change in load, this mechanism does not work well. However, in the figure 9, what I have illustrated, the position of nozzle for a full load and for a part load. What has been observed that the needle is moved inside the nozzle, blocking the opening of the nozzle, and thereby the effective flow area has decreased, decreasing the flow rate and hence the diameter of the Z with respect to the full load. When a sudden change in load occurs, a more rapid response is needed. This is accomplished by temporarily deflecting jet with a deflector plate as indicated in figure 9b. Please note that there is a deflector here, and when a sudden loss of load occurs, with the help of the deflector, the jet is deflected here, not allowing to pass through the buckets. Thus, this deflector prevents over speeding and allows time for the slower acting spark valve to move to its new position. I've already illustrated earlier that specific speed is very important parameter in turbomachinery, which is the single parameter that characterizes the kind of machines. Furthermore, it can also be related to the design of the machines. Here also, the specific speed can be related to the Pelton turbine design. Thus, in this section, I'll tell you how the geometric parameter of a Pelton wheel can be related to its specific speed. With respect to the specific speed and wheel geometry of a Pelton wheel, I'd like to say that the specific speed of a Pelton wheel depends on the ratio of jet diameter small d to the wheel pitch diameter capital D, where capital D being the diameter of the circle at the center of the bucket. Here, the hydraulic efficiency of a Pelton wheel is defined as eta H is equal to P divided by rho Q G into H, where P is the power, rho being the density, Q is flow rate, and H is the head available. So thus P can be expressed as eta H rho Q G into H as stated in equation number 20. Further, I can write Q is equal to pi d square small d square divided by 4 into C1, where C1 being CV into root over 2G into H. The rotational speed of the wheel can be expressed also as U blade speed divided by pi into capital D. Now, the specific speed for the optimum condition of the Pelton wheel can be expressed as Ns is equal to N root over P h to the power 5 by 4. Now, putting the value of P, N, H in terms of C1, I can show that Ns is equal to some constant into D by capital D, where small d by capital D represents the jet diameter to the wheel diameter. So please note that specific speed for a Pelton wheel at optimum condition can be expressed as some constant into small d divided by capital D. Following correlations are established for maximum achievable efficiency considering the past work and available data on the Pelton wheel. Thus, capital D by small d, that is ratio of wheel pitch diameter to jet diameter, can be expressed as 206 divided by ns, where ns being the specific speed, and here n is expressed in rpm, p in kilowatt, and h in meter. The number of buckets required to maintain the optimum efficiency is usually decided by another empirical relation as n being number of buckets is equal to 15 plus 53 by ns. Please note that capital D by small d, that is pitch diameter of the wheel divided by jet diameter, is an important parameter. A large value of d by small d reduces the RPM as well as the efficiency of the wheel. Furthermore, a lower value of capital D by small d increases the specific speed, but the efficiency will again decrease because of closer spacing between the buckets. Thus, the value of capital D by small d is usually kept between 12 to 16 to maintain high efficiency. So these are the few facts based on which a Pelton wheel is designed. Let me remark now about limitations of a Pelton wheel. The Pelton wheel is efficient and reliable when operating under large head. To generate output power under a low head, the flow rate through the machine has to be higher, which requires an increased jet diameter. The increase in jet diameter in turn increases the wheel diameter. Therefore, the machine becomes unduly large, bulky, and slow running. In practice, for a lower head, we push to reaction turbines which are more suitable for low head. In this chapter, I have discussed about the Pelton wheel, its construction, function, and how to derive the power output and the blade efficiency. Furthermore, I have correlated the specific speed with the wheel geometry and thereby the correlations which are used in practice to design a wheel. Hope the lecture is helpful and you have enjoyed. Thank you for listening.